Welcome to the webinar today. I'm Matt Cederberg, the Coreform Chief Strategy Officer, and I'm joined today by Dr. April Novak, Assistant Professor at the University of Illinois Urbana-Champaign and the lead developer of Cardinal, and Dr. Patrick Schreeweiss, who's an Assistant Computational Scientist at Argonne National Labs and a developer for OpenMC and DagMC. Today, we'll be introducing a nuclear multiphysics workflow using Coreform Cubit, OpenMC, Moose, and Cardinal. We're excited to bring to you an accessible, high-fidelity nuclear multiphysics workflow. The motivation behind this is that multiphysics analysis is really helpful to properly account for the interaction between radiation transport and other physics areas when doing nuclear engineering. But the industrial use of multiphysics has really been limited to date because of a number of issues, including tedious software dependencies, incompatible data representations, and workflows that require you to be an expert in the creation of that workflow to actually run it. But we've made a number of advances over the last while together with Coreform Cubit and then showcasing also advances in OpenMC and Cardinal that enable this multiphysics workflow to be more accessible now. The learning objectives of the webinar today is to learn how to run a multiphysics simulation with a single source of truth geometry representation. So the key value points here is the elimination of tedious software dependencies. And we will be sharing a short list of the required software needed to run this workflow at the end of the presentation with hyperlinks that we'll share out. We are introducing a workflow that doesn't have incompatible data representations. So what we'll be showing is how Coreform Cubit can be used to create a single source of truth, where we take in OpenMC constructive solid geometry data and then convert that to CAD and then use that to generate the meshes and the surface meshes that will be used for the nuclear multiphysics. This workflow also enables the full 3D data visualization, which is an enhancement over the 2D slicing that's often used to visualize CSG data. The workflow is much more straightforward, and so Patrick will be showing a new step-by-step DagMC toolbar that's he developed for Coreform Cubit to have all the commands needed for this workflow. And then there's also improved DagMC documentation to make this more accessible to outsiders. And again, all of the data and the tutorial from today's webinar will be available for you to reproduce yourself and to try out this multiphysics simulation with a single source of truth after the webinar.
Excellent. Thank you, Matt. So for today, we're going to be doing a couple of things that Matt already mentioned. We're going to be working with these new integrated DagMC functionalities in Coreform Cubit, and we're also going to be using a tool that allows us to convert a neutronics model into a CAD model that can be imported into Coreform Cubit. And then once we finish some setup and some meshing of that resulting CAD model, we're going to be doing a solution in Cardinal using some multiphysics, where Cardinal is supporting OpenMC and NeckRS within the Moose framework. We're not going to be running NeckRS today per se, but that is a capability that's built in with Cardinal. And the demonstration model we'll be using is a representative model of the Krusty reactor or the kilopower reactor using Stirling technology. This is a spacefaring reactor for power on a spacecraft. And so we'll be doing all of this kind of centered around Coreform Cubit as a preprocessor for a neutronics model and for a Cardinal model as well. Coreform Cubit supports a number of different operations related to CAD and meshing, anything from cleanup to semi-automated meshing, control and evaluation of mesh quality. The big highlights for us is for today's work is Python and scripting. The DagMC toolbar leverages a really powerful capability within Cubit to extend the GUI so that it makes these operations a little bit cleaner and a little more transparent. And then we're also going to be highlighting how it can be used for OpenMC, and MCMP workflows have been covered in previous webinars, which are linked here in the slides that'll be available at the end of the session. So some of the software we just wanted to cover in addition to Cubit that's going to support the tutorial that we're working on today. One of them is DagMC, and DagMC is an interface to support particle transport, Monte Carlo particle transport on CAD-based geometry. And it does this by starting with a CAD model and producing a surface tessellation. There formerly was a tessellation sealing step that is now kind of obviated by the ability to tri-mesh directly in Cubit and produce a watertight mesh that you can see on screen. We'll be doing that today. We'll talk more about it when we get there. There are several different capabilities for supporting CAD-based geometry in the Monte Carlo world. The one that I think sets DAGMC apart is its ability to represent embedded geometry topology for more robust and efficient transport during Monte Carlo operations. And this interface is supported in a number of different codes. We wanted to mention, this isn't an exhaustive list, but this is probably the most well-known set of codes that supports DAGMC interfaces. And today we'll be working with OpenMC in particular. And so OpenMC, if you're not familiar, is an open source Monte Carlo particle transport code. It supports programming interfaces in C++ and Python. So mostly the heavy lifting, if you will, of the computational work is done in C and C++, but with a Python interface. And in addition to a Python interface that can interact with those C and C++ kernels directly if needed. It supports operations for interfacing with nuclear data, and it has its own representation of that cross-section data in an HDF5 format. And you can build those yourself with the Python interface as well. It does support depletion also through a Python module. And primarily our focus in development of OpenMC is in terms of building capabilities that support a broader community, as well as on the research side, more so HPC support. So looking at things like supporting transport on GPUs. And one thing that we're, in terms of that broader support and flexibility that we'll be looking at today is the ability to support hybrid CSG-based geometry and CAD models in the same OpenMC space.
So I want to introduce how all of this software is going to relate in the context of this webinar. So we are going to be showing a demonstration using Cardinal. This is a Moose application developed under the Nuclear Energy Advanced Modeling and Simulation Program, or NEAMS, which couples OpenMC to Moose using CAD geometry. So the idea here is to really do integrated physics simulation of different nuclear systems, both fission and fusion. And so a typical use case would be anything where neutron transport could affect other physics, such as through heating, material damage like DPA or fast fluence feeding into material property correlations, environment characterization, and the reverse, if any other physics influence your neutron transport, like changes to cross-sections from temperature and density and geometry motion. And so a typical use case is shown here on the top right. This is a fusion breeder blanket module where you might use OpenMC radiation transport to solve for neutron photon movement through materials, which provide a heat source term to a Moose-Navier-Stokes module application to solve for fluid temperature and velocity and movement of materials, which feeds into a solid mechanics module to compute stresses and strains and temperatures in your solids. And so Cardinal provides this integrated environment, which is going to take CAD geometry from OpenMC, generated from Cubit, together with ray tracing with DAGMC, all to do this very integrated type of multiphysics simulation. Typical use cases for this software for industry would be for system design, providing reference solutions that you might use for benchmarking coarse mesh tools or providing validation data, and creating constitutive models like multi-group cross-section libraries, heat transfer coefficient correlations, and so on. There's a few different types of geometry we'll be generating and preparing for this Cardinal simulation using Cubit. And there's two main categories. So we'll be generating a DAGMC geometry within which neutrons and photons are going to move. And so that will be a triangulated surface mesh, which Patrick already introduced, which will enclose bodies of space. And so this bottom left image is a rendering of what that would look like. And so we'll generate this triangulated surface mesh with Cubit with the DAGMC plugin. We will also generate volumetric meshes for which we will tally the output from OpenMC, so obtaining a heating distribution, fission reaction rates, tritium production on a volumetric mesh. That data then gets passed to another volumetric mesh where we are solving some type of finite element calculation with the Moose framework. And so that could be fluid flow, heat transfer, solid mechanics, material science, whatever physics is relevant to your problem. So two meshes we will generate today, a surface mesh and a volume mesh to fulfill these needs. A main feature of what we're covering in this webinar is a new feature in Coreform Cubit for importing CSG geometry. Many people who work a lot with Monte Carlo methods are very comfortable and familiar with CSG geometry representations, this Boolean primitive combination of surfaces to construct space. However, this is inherently in contradiction with a lot of multiphysics workflows which start from CAD. And so what we're going to show is how we can import an existing CSG model into Coreform Cubit to generate CAD, which you can then use to generate meshes for multiphysics. You can use that for 3D visualization, removing a lot of the complexities of 2D slice plots, as well as for propagating to other engineering domains. And so the real strength here is that we are having now a single source of truth or a single common ground of information feeding into these different workflows, which is really powerful from personal experience working with these multiphysics complex stacks. Other useful features that we will show you are partial model conversion. So being able to load a model into Cubit is really useful for debugging geometry or complex parts, building a complex model pieces at a time, so interactive model building, as well as for visualizing lost particles when you have more complicated models. So we are going to be doing a simplified version of the Krusty reactor. This was a fission reactor built and operated at Los Alamos National Laboratory. There's a photo in the top right of the fuel region. This is the region that we will be converting from CSG into CAD. And so it's a cylinder. It's about a foot high, and it has 8 smaller cylinders kind of drilled through the side where there are heat pipes removing the fission energy. So in my group, we have an existing very detailed CSG model of this geometry for my student, Michael Mendez, and that's shown here in the bottom left. And so there's a lot of components here. It comes from a benchmark representation of the figure shown in the lower right. And so we have the CSG model, and we want to do multiphysics on it now. And rather than trying to recreate this from scratch separately with CAD, we're going to load this in, generate the CAD that we need for multiphysics, and then run it through Cardinal with coupling to Moose. So our objective here is to couple OpenMC neutron transport for the fuel region to a Moose finite element heat conduction problem. So for the purposes of this webinar, we're doing a simplified but still representative version of the Krusty reactor. So instead of the fully detailed model, we're going to take a slice through the middle, and we're going to really focus on the fuel region. So this slice here is going to be this cylinder. We're going to see this inside of Cubit when we import it. And we're going to be doing multiphysics on this dark mustard green region, which is where we have our metal fuel. So this CSG model will be loaded into Cubit as CAD. And so it's going to have a rendering which looks like this. Patrick is then going to take this and generate 2 different meshes from this. We're going to generate a surface mesh of the fuel, so converting a single cell from CSG into DAGMC geometry. So that's shown here in the top right. And we will also generate a volume mesh for tallying power and for solving heat conduction. And one thing that's really powerful about this workflow in Cubit is that these meshes have the exact same boundary mesh. And so they're exactly conformal. They can serve volume and mass, which is really important for these types of criticality applications. And it just makes data transfer so much more straightforward.
Okay, so to set the stage, just like April mentioned, we're kind of in a world where we have an OpenMC neutronics model, and now we want to extend our analysis to some multiphysics application. And what we're trying to support here is a situation where we don't want to have to duplicate effort and redefine the geometry or material assignments of this model in CAD separately in Cubit. So like going back through our CSG representation and figuring out what parts we need to make. Instead, we've attempted to automate that process. And that's what we'll be starting with today. So a little bit about these formats, just in case we're not familiar. The XML files here are, as we'll look at the original model, which is our full CSG model of the Krusty core, are XML that can be interpreted by OpenMC and used during transport. This format is more human readable than some that you might experience in the Monte Carlo space, working with different codes, but it's still not one that we can easily parse and understand, especially in terms of the geometry when we see things like our cells and defined as regions that are these Boolean combinations of half spaces on each side of the surfaces that we support in OpenMC. There are tools that make it a little bit easier to explore these models. In particular, there's the OpenMC plotter. So if I apply that to the original model and start that up, oops, did I misspell something? So if we pull this up, there is a GUI application that supports visualization of OpenMC geometry, and it's somewhat interactive, which is really nice. And we can visualize different components and move through the model relatively easily, as well as view things like the different materials and change their colors as well. So if I find one here, I can customize the imaging that I see here. And we have some limited support for tally visualization here as well. This tool is being continually developed, but as you may have noticed pretty quickly, it's limited to 2D slices through that geometry. And as components become more and more complex, it can be difficult to navigate mentally where we are in the model and what those components truly look like in a 3D virtual space. So that's definitely a good thing to have in a toolkit for neutronics. But as we extend this to CAD, and in particular for meshing, we really need some kind of CAD representation. So I'm just going to clear my terminal out here. And so this is where what enters a tool that we have that is called the OpenMC CAD adapter. So this is a tool that has a very light software stack. In fact, I think the only primary dependency is OpenMC, the Python API itself. And so installing it is extremely simple. The instructions for this will also be included in the Cardinal tutorial. But in one line, I can go ahead and install that tool. And then looking at what we have in our directory again, I can take a look at the options for the resulting program that's installed with that Python module. It's just called OpenMC to CAD. So there's a number of options here, but the primary required argument is the path to a model file that we have here in our original model is what it's called, or a path to a directory containing a set of OpenMC XML. So if you're familiar with OpenMC, you can either provide a single model file that contains all of the necessary components, or they can be separated out into multiple XML files for tallies, settings, materials, and geometry. There are some other arguments here that are important. The ones that I want to highlight is the world size. So when we're translating models from CSG space into CAD, something that CAD does not deal with very well is infinite regions. And so what we need to provide here is a bound for our geometry. This can be conservatively large, although I wouldn't say like you need to make it orders of magnitude larger than your model, but something conservative is sufficient. We will try to determine a finite bounding box for the OpenMC model, but some surface types like quadratic surfaces can make that really difficult. And so we have this option to provide that manually. The other option I want to highlight is the ability to convert single cells. I'd say this is something that distinguishes this tool from similar ones, such as MCMP to CAD, or the ability to import MCMP models into Cubit, which I can touch on a little bit, and actually has been demonstrated in previous webinars, and that's probably the place to go to look for that. But what we can do here is provide a list of cell IDs that can be converted separately from the rest of the model. So if we're really only interested in coupling a single volume or a single part in our model, we can isolate that and bring it into Cubit separately. Or if we just want to look at subsets of them to make sure we've defined a particularly complex cell correctly. So to use this command, we'll go ahead and run it, OpenMC to CAD. I'll provide the model file that I would like to convert. And then I'm going to say that the width of this model is 1,000 units. 1,000 units by 1,000 units, or the world size of my model. So that's much larger than we really need it to be, but that's just fine. Those model units being centimeters in OpenMC, and in Cubit, it doesn't really have a notion of units, just for reference. It's just model units. The cell ID that we're going to be interested in is just cell 1. So upon interrogation of the model, we can figure that out. You can use the plotter to do something like that, for instance. And so when I run this, it's going to pretty quickly generate some files for me. The new files that we have here are OpenMC, which contains the entirety of the model, and then OpenMC cell 1. So this is just the single cell ID with ID 1 that's been converted into this journal file. And so these journal files are a set of Cubit commands that can be played back within the Cubit GUI to produce a model. And you can additionally, if you have the Cubit Python module installed, you could run a Python script that would generate your CAD model within Cubit and then export it to some other format that you're interested in, like ASYS or STEP or IGES or what have you, or the Cubit native format as well. And so really, now that we have these, we have essentially what is a CAD component that we can start looking at. and playing with inside of Cubit. We can go ahead and bring these models into Cubit. We're going to go ahead and view the full model and make sure I'm in the right directory here. Okay, looks good. This is extremely useful, so we can just kind of experience that interactive capability to view the entire neutronics model in CAD within Cubit. So if I play back the OpenMC journal file that contains the entire thing, it'll take a second, but we can see over here the model tree is updating with the material assignments for the different regions within our CAD model. And those components are being brought in, and here they are. When these volumes are created, the surfaces are not imprinted and merged by default. That's something that we leave to the user to do because there are scenarios where maybe you don't want to merge everything. But in this case, we're going to do imprint body all, and then merge body all. And that'll just clean up the graphics for us a little bit for the purposes of this section. But this allows us now to visualize the entire geometry in CAD. We can slice through it. We have this interactive capability to examine things. And importantly, our material assignments have been preserved. So if I really want to isolate one particular region of the model, I can do so very easily. So for example, our fuel region, which is our region of interest for the multiphysics coupling we'll be doing in a little bit. So now that I've done that, we don't need this whole model. So if I bring everything back, we don't need everything that we see here for the purposes of this application. So we're going to go ahead and just run reset in our command line console. And then instead, I'm just going to play back. And actually, I'll do this through the GUI this time. So we can use the console to do journal playback like this, but there's also a button up at the top here, which is a little piece of paper with a play button on it. And that will open it up through the GUI as well. So this is maybe a little bit more of an accessible way to do that. And instead, this time I've selected just that OpenMC cell 1, and that's brought in a single volume, again, with its material assignment into Cubit for us to use. Okay, so this is a really handy capability. Again, super useful for debugging, just for the pure purposes of visualizing these volumes in 3D. But now we can take that a step further, and we can take our originating in a neutronics model, we can start to build up a multiphysics coupling mesh. And so the first thing that we're going to do is build a DAGMC surface mesh. We'll be doing this with the Cubit tri-mesher. So in the GUI here, I've selected mesh. We'll just start over and do that. We'll go to mesh. We've selected surface mesh, and we'll be using the tri-mesher in particular. So we've imported the only volume that we really need. So we can just say for the surfaces that we want to mesh, we're going to be meshing all of them. I tend to check this box that's the split over constrained edges. This will insert new triangles when needed if some of those edges are causing conformity issues, like along the curves. I do want to highlight that we are not using the coarse mesh settings that we've used in previous webinars. This is because we want the triangles generated in this step to be a little bit, to have aspect ratios that are a little bit closer to unity, and in turn produce a cleaner TEP mesh for us in a subsequent step when we do the volume mesh. So I'll go ahead and apply that scheme, and then we'll create our mesh. And that's really all there is to it. I will reiterate from previous webinars, I've mentioned that this is a capability that has not been present before up until recently in Cubit, to be able to visualize the actual mesh that's being created in DAGMC. However, one thing we did lose for a while with this workflow is the ability to specify what our approximation is, or understand what our approximation of the analytic surfaces is when we perform this surface meshing. And so what we've added is a DAGMC toolbar. Up here, this toolbar adds a few different buttons into Cubit. This is something that needs to be added on to Cubit when you download it and install it. There's a package that will provide that includes instructions for that. And it's relatively straightforward and can be done almost entirely through the GUI. But one of the tools that we can use here is what's called a faceting report. And so when I click this button, it's going to go through the entire model and determine what's the faceting approximation, or the maximum distance from a triangle to the analytic surface in CAD. And what this allows us to do is at least to understand where we might want to refine some of the faceting of those surfaces if we feel like the approximation is too high. And we do get some surfaces like planar surfaces here where our faceting approximation is essentially 0. And also here on the bottom of this volume as well. We added this ability to highlight the different surfaces in the table. So if there's one in particular that is, so that you can understand if the faceting approximation is surprisingly high, whether or not it's going to be impactful for your simulation as well. And those surfaces can be isolated if they're deep in the model or inspection. Okay, so I'll bring all of those back. That's really useful, I think, to be able to understand our approximation of the geometry itself. But there are other capabilities that we'll be using here today. When these models are brought into Qubit, they're assigned materials based on a group structure that supports a legacy format for DAGMC when exported through Qubit. But we've been moving to one that is a little bit more integrated with the natural data model for material assignments within tools like Qubit. And so to translate these material assignments into that data model, we've added a tool here, which translates our group assignments to block assignments for DAGMC geometries. And we just added this little intermediate step to make sure that all the groups are identified correctly. And that there may be some groups you aren't interested in converting because you're not interested in using those volumes for the subsequent CAD model. But upon clicking convert, when we look at the model tree to our left, we'll see that a new material has been added with the same name that was specified for this group above, and then also a new block for our DAGMC geometry. Now, we're really ready to go ahead and export this DAGMC geometry, which we can do again through the GUI. If I select here, I'll go down to the DAGMC format at the very bottom. And I'll just call this crusty fuel.h5m. Sit finish, and out it goes. So that's our DAGMC model created. Now we're going to do the second step that April mentioned earlier, which is to create a volume mesh that is going to allow us to tally heating and also couple to the external heat conduction solution that we're going to be performing in Cardinal. The first thing I'll do is just go ahead and remove this block. We don't need it. The assignments for the volume mesh that we're producing are just simply different. So I'll remove that block and I'll go ahead and delete this. So one opportunity that this presents us with, the ability to mesh both the surface mesh and the volume mesh in the same space, is the ability to ensure that all of the boundary triangles of the DAGMC mesh are going to correspond to the boundary of a TET mesh that we generate here. And so we're going to generate this TET mesh using just the TETs ability, and then there is a mesh triangles feature. And so what this allows us to do is select a set of triangles that will then be volumetrically meshed into a TET mesh. And for us right now, since we only have one part, we can just say we want all of the triangles of this mesh to be used to generate that TET mesh. Now, if there were like multiple volumes and we only care about volumetrically meshing one mesh, then we would need to adjust these settings, of course. Okay, and so now, just like that, we now have a volumetric mesh. I'll go ahead and slice through the model so we can convince ourselves that that's true. So when I select that block of the mesh, we see that we have kind of components filling that space in between the surfaces. And when I deselect it, it's now hollow. So bring that back one more time. And so that's really all there is to it. We now have a mesh that's going to exactly align with our DAGMC geometry. And the last step that we need to do is provide a little bit of information to Cardinal so that it can identify specific regions of that mesh that it's going to be using for the multiphysics coupling. And so here we're going to be adding a side set. And that new side set name is just going to be called heat pipes. This is the name that Cardinal is going to be expecting to find on this mesh for the side sets. And April will go into more detail about that. Now, we only want to apply this to a specific set of surfaces. I'm going to remove my clip here. If we look at our surfaces, we really only want to apply this to surfaces 233 through 234. Or sorry, through 240. I'm scaring April right now. And so these are the boundaries of this fuel volume where they're going to be interacting with the heat pipes that slot into these gaps. And so I will specify that I want my side set to be set accordingly. So it's going to be surfaces 233 to 240. Apply it as such. And I'll just double check real quick. We do have a new side set that is the heat pipes. It's applied to those surfaces. And then I can send this model out. So I'll do export. And this time we want to export this as an exodus mesh, a volumetric mesh, across the fuel.e. We'll save that. And off it goes. And so now if I look in my terminal real quick, I now have these models, crusty fuel and crusty H5M. And those are the two meshes we'll need to do our multiphysics coupling.
Okay, so Patrick made us the two meshes that we need now to do multiphysics coupling. So I'm going to describe what we're going to do and one unique feature about Cardinal, which adds on top of this really powerful qubit workflow to make this even more approachable for multiphysics. So again, we have now an OpenMC model, which is going to be hybrid CAD and CSG. So there will be a DAGMC model of just the fuel, but we're going to retain everything else as CSG. So this is really powerful if you want to do just component-wise multiphysics, or maybe just build up a modeling complexity so that you're not trying to model the entire thing all at once right out of the gate. With this OpenMC model, we're going to be computing power on a volumetric mesh that will then get passed to a Moose heat conduction finite element solver. On that mesh, shown on the right, this volume mesh, we're going to solve for temperature. That temperature will then pass back to OpenMC in order to change cross-sections from Doppler broadening. And so the heat conduction solver, we're just going to be solving a pretty simple steady state heat conduction, constant thermal conductivity using Moose. So one thing that you may be wondering if you're very familiar with multiphysics with Monte Carlo methods is how exactly we use changes in temperature to update cross sections. OpenMC, like many other Monte Carlo codes, requires your nuclear data, your cross sections, to be constant over individual cells. So this is an image of the temperature we're going to predict with Moose, which is clearly not constant over this geometry. It's continuous, varying in space. But the geometry we obtained from Qubit was a single cell, a single CAD body. So what we do in Cardinal here is that we actually contour the initial qubit mesh that we take according to temperature feedback in order to, on the fly, make our cells smaller and smaller to resolve temperature feedback correctly. And so this is shown here. We're going to do a very, very coarse contouring interval so that this is a little bit easier to see. But if this is the temperature we're going to obtain from Moose, we are going to, on the fly, change the geometry in OpenMC by essentially contouring the volume mesh into new DAGMC surface cells. And so this temperature might produce two cells if we contoured by temperature here, and this GIF on the right is kind of showing you a view of what this peripheral cell looks like. So it's a 3D new cell we're creating on the fly. Okay, so the files I'm going to walk you through, I'm going to do a really quick walkthrough of our heat conduction input file and our OpenMC input file. These are going to be based on Moose type syntax. And so what you'll see is a general structure on the left. We're going to have square bracket blocks that cover the major building pieces of a simulation. So the geometry we're using in a mesh block, what variables we're solving for in a variables block, what equations we're solving in a kernels block. We'll build those up piece by piece in our differential equation, any boundary conditions we may have, and so on. So what I'll show you is how do we specify the mesh geometry for a Cardinal application? How do we define the physics of the problem? So the fields we're solving for, the equations, boundary conditions, some initial conditions. How does the data passing happen? And some solver options. And so this really requires like a full workshop on Moose to really understand all of the options I will be showing you. So I'll be going quickly, but my contact info is at the end if you want to learn more. Okay, so let me switch to my terminal. Okay, so the files that I'll be showing you, they're in this Cardinal tutorial CSG to CAD folder, which has these files, here. So all the files that I'm going to be showing you today and that Patrick has already shown are hosted on the Cardinal website. If you go in the Documentation Tutorials tab, at the bottom, there's a new section here, Converting CSG to CAD. And so what I'm going to walk through quickly is the information on this page. So it includes a summary of what Patrick already showed in Cubit, but also discussion on how we build a Cardinal model and what all the Moose parts mean. So I'm going to start by walking through the input file we built to solve for heat conduction. So let me maybe describe the structure a little bit first. We're going to have two different input files, one for each physics. For the problem we're solving today, we have heat conduction physics and neutronics. So we're going to have two different files. Each of them are going to solve their own set of equations and pass data to one another. They're going to be coupled iteratively. So we're going to solve OpenMC to predict power that will get passed to our heat conduction solver, which uses it as a power density. That solver will then compute temperature and send it back to OpenMC. So when we go to run these files, you're going to see that back and forth solution of OpenMC, solution of Moose, where they're then passing data under the hood. So the input file that contains all the heat conduction information is called fuel.i. This is a name that you're allowed to pick as the modeler. And so here we see this type of block structure that I just introduced. At the top, we are using that volume mesh that Patrick generated. So we're going to solve for heat conduction on that volumetric mesh. We will solve for a variable called capital T. This is what I'm going to call temperature. We will obtain power from our separate OpenMC solve. It's going to be written into what's called an auxiliary variable, which is typically used for passing data. It's not something that is solved by our heat conduction solver. It's kind of like a receiving point for field data. And so this power field is going to be populated by OpenMC. The physics we're solving are steady state heat conduction. So this heat conduction kernel, that represents our Laplacian term, and this coupled force term, that's our heat source term, so our body force. For our boundary conditions, we're just going to do a simple Dirichlet condition of 800 Kelvin on that heat pipe's surface that Patrick created. This is a decent approximation for heat pipe heat transfer, keeping the model simple today. We need to provide a material property for our thermal conductivity. We'll just use a simple value here, 0.1. All the units that we're doing today are in centimeters as our length scale. When we pass data between OpenMC and Moose and back and forth, it's really important to ensure conservation. So for us in this application, that means conservation of power. And so when we pass these field data around, we do an integral of power from the mesh it's computed on to the mesh where it's received and make sure that we normalize everything so that we're not losing or creating any power. And so this post-processor here will be doing that type of volume integral. And we'll see a similar sister post-processor when we talk about the OpenMC model. Lastly, we're going to run this as a transient problem, which means that we're going to run it multiple times. And we are going to generate an Exodus output file, which will contain all of our results. So our finite element temperature field, the value of the post-processor, and so on. Okay, so we have a second file called openmc.i. Again, a name that you get to choose. Here you're going to see a similar block structure, but a little bit different. This is the Cardinal input file. And it's here that we are essentially replacing finite element capabilities of Moose with calls out to OpenMC. So the most important part of this file is this problem block, and that's where this replacement is happening. We're telling Moose, bypass the typical finite element solve that you do. Instead, let's call a k-eigenvalue simulation from OpenMC. So all the settings in this block refer to tallies we create in OpenMC, information on how to normalize them into units useful for multiphysics, and maybe some run settings. So we're going to assume a constant power of 3 kilowatts. We're going to apply temperature feedback from block 1. That's the fuel block that Patrick created. We're going to run with a relatively low number of particles for this tutorial, just so that it's a fast run. And then here's some information on the tallies we're creating. So we'll create a mesh tally. It'll be tallying on that volumetric mesh, which Patrick created. And we're going to score our neutron flux, as well as the power deposition with a kappa fission score. That tallying happens on this mesh. Again, this is the identical volumetric mesh that we're using for heat conduction. The contouring of geometry happens with something called a Moab skinner. So this is using the mesh library built into DagMC. And here in this block, we specify that contouring setting. So we're going to contour pretty coarsely just so that we can visualize this easily. But we're going to group elements according to intervals of 50 Kelvin and create new OpenMC cells on the fly. All of the multiphysics information happens in the multi-apps and transfers blocks. So it's here that we are going to have OpenMC spawn a heat conduction solve, which runs on every time step. The transfers block then tells how the data is going to move. And so the information you'll see here is what type of data transfer are we doing? There's many options in Moose, like nearest node. Here we're going to actually evaluate shape functions as we pass between. The rest of the information may be what are we conserving when we pass that data? And so we're conserving power in this case. And what are the names of the variables in the source file where they are computed to where they are received? At the end here is just a little bit more on the initial conditions we need to set for temperature and power, just to make sure that all of our solvers have good starting values, a post-processor to compute the integral of volume of the power, and again, our settings for how to run this. And so we're going to run OpenMC 3 times. So we're going to run OpenMC heat conduction, OpenMC heat conduction, OpenMC heat conduction. And that will be the simulation that we do. Okay, so to run this, I'm going to use the Cardinal executable, cardinal-opt. That's the optimization setting that it was compiled with. And I just pass it the name of the file, which is controlling the coupling. And I'm going to run this with 40 threads, just so that it goes kind of quickly for the tutorial. So we first start out, OpenMC initializes. If you've watched past webinars, you're probably familiar with this logo and the information that prints out here. So it's going to tell us where are we getting our nuclear data from. Then it's going to start to initialize Moose. And so you'll see information on the meshes that we're using. The volume mesh that Patrick created has 134,000 elements in it. And so we're going to have a tally with 134,000 values that we're tallying. Then we'll initialize the heat conduction solve, which in this demo is using an identical mesh that we're using for tallying, though this is not strictly necessary. And you could use a finer or a coarser or different element types even for more flexibility in multiphysics. Cardinal then prints out some information about the geometry mapping. And what's really nice is that when you have this CAD geometry, which is exactly identical boundary-wise to the volume mesh, there's really not any debugging that you need to do here. These types of tables are really important when people are building CSG multiphysics models, because it's very easy to have a misalignment, lack of volume conservation. And so we can kind of just skim past these. This makes our life a lot easier. So then we're going to start our first OpenMC solve. So we're going to do our inactive batches and then move to our active batches, where we're doing a K eigenvalue simulation. And then we start our heat conduction solve. So Cardinal's passing that data under the hood here. After every solve, we are going to regenerate the OpenMC model. So it's here that that contouring is happening. This could change every iteration in response to the temperature field, how it's evolving. And so we're just going to run OpenMC again, run heat conduction again, and it looks like it's working right here. So let me switch over to pair review where I have the files. I think that we have the idea of how this is working. So I use pair review for visualization. This is free software where you can open up meshes with field data on them. So what I've opened here are those Exodus files that will be created by Cardinal. And so I have here the output file, which has the heat conduction solve, and I have the output file, which has all the OpenMC information in it. And so I'll start with the heat conduction solve. So this is the mesh that Patrick created. I have it just colored by a solid with the surface with edges here, but I can look at the temperature field that is computed by Moose. Maybe let me turn the surface off and rescale that. And so here is the heat conduction solution coming from Moose. The power from OpenMC is really driving this. I could do a few clips to look inside. Let me rescale again. And so I can see that it looks like my power might be kind of peaked a little bit downward. This isn't exactly symmetric here. And so that's coming from the details of the neutronics geometry. Let's see, I have another clip here. So we can see it's very hot along the center because all of the cooling is happening here along these heat pipe boundaries. So this temperature is what gets passed to OpenMC. So let me open up my OpenMC output file. So this is, again, the volume mesh where I'm tallying fields from OpenMC. Let me take a look maybe at my power deposition. And let me hide that. Okay, so this is the mesh tally coming from OpenMC. This is the kappa fission score. So this is the recoverable energy release from fission, assuming it's all deposited locally, right, where the fission event happens. And so I can see it's very peaked along the periphery from the reflector, reflecting back some neutrons. So remember, there's a CSG geometry outside of this big DAG-MC component. And I can take another clip. Let me put them both on kappa fission. And so I can see now the power that's coming from OpenMC. I also can have other tallies like flux. Let me change both of these to flux. And so this is my total neutron flux in this problem, which you might use then for computing reaction rates. So this power, this kappa fission, gets sent to the heat conduction solve and used for the temperature computation. So if I turn back over to the temperature file and back in the fuel output file here, I can look at the OpenMC model, which is recreated on the fly. And so what I have here is I have some of that contouring opened. You can output this file with some additional settings in Cardinal. And so what I'm showing you here, all these gray surfaces are the boundaries of the OpenMC cells that we are forming. And so you can see we have this new cell formed in here. That region is a lot hotter than the cell out here. And then those are going to each be set to some type of constant temperature. And that's fully tunable. You can control that contouring so that you can basically control how resolved is the multiphysics that you are having in a Cardinal simulation. So thank you everybody for joining this webinar. All the software stack that we demonstrated today is summarized here on the left with links. So just to recap, we use Qubit to generate geometry for Cardinal simulations. We also use the CAD adapter to take an existing CSG model of OpenMC, which my group had developed as part of a criticality benchmark exercise, which we then wanted to extend to multiphysics. So we use that adapter to load the geometry in, to inspect it, to see it in a 3D sense. And from that single source of model information, we generated an exactly conformal surface mesh for a volume tally mesh. The model we generated was also hybrid CAD and CSG. So we had a DAG-MC model of just the fuel with CSG on the periphery. With the Cardinal simulation, we built a heat conduction finite element solved with Moose and coupled that to OpenMC. So the webinar material is all freely available online on the Cardinal website. I showed you the link earlier, but here it is again to go directly to that tutorial. All that you need to run the tutorial is Cardinal. So we will provide the mesh files we generated with Qubit if you don't yet have Qubit. And then the full workflow is open source. I also wanted to mention that there is a free version of Coreform Cubit, which is really great for trying out this workflow and seeing if it works for the analysis needs that you have. If you have any questions on the webinar, we've created a discussion page on the Cardinal repository. So Patrick, myself, and Matt will all be hanging out there to answer any questions that you might have, whether it's about any of the software tools we talked about or how to compile them, anything at all related to this webinar. Lastly, I want to mention, we really want to get this software into your hands. We're really excited and want to engage with industry applications of these advanced modeling and simulation tools. So our contact information is down here. Please get in touch with us if you have ideas or ways that we might help accelerate your technology development. There's lots of programs within DOE such as GAIN or Infuse or SBIR that are really great avenues to support industry use cases. And so get in touch with us if you think that there's a way that we can help with your workflows.
Thank you very much, April and Patrick. So this is a question from Kent, going back to Patrick's part of the demo. If the surface mesh and volume mesh have the same conformal mesh, I guess that means that only tetrahedral meshes are supported for volume tallies. And are there any limitations from that?
Yeah, that's a good point, and that is correct, right? So for the workflow that we demonstrated today, where we're using that tally to generate subsequent geometries for the neutronics, is supported only for tetrahedral mesh. That's right. There's no reason we can't extend that to other linear mesh elements pretty straightforwardly. Getting into curvilinear is a little bit trickier. But that is the current extent of the feature. Yeah.
I do want to add on to that, though. Like OpenMC does support tallying on
sorry, that
other
was
element
another point.
types. It just won't be exactly conformal with the surface mesh.
Right. Yes. Yeah. So for for any of the element types that's supported by, in particular, by libmesh, so you can perform tallies on those different curvilinear element types. It's just going to be limited to a collision estimator. We can't do track length estimators quite yet in OpenMC, but you can do tallies. Yeah.
Okay, thanks. Another question from Ken. What is the minimum qubit version that this workflow works with? He notes that the Python API has been around for a while and that watertight meshing has also been around for a while. So what is it? What is it that's new that's enabling this workflow, and which version of qubit is that supporting that supports that?
Yeah. I guess as far as the workflow goes, like the ability to generate journal files is kind of agnostic to the qubit version. So for that component of the workflow, that'll go back as far as that is supported. And for the DAGMC component of it, where we're exporting the DAGMC model, I think that came about in like late last year. I think I'd have to go back and look at the release notes, but I want to say like 2023, 11, maybe earlier than that. But that's approximately the time range.
Yep. Great. Thanks. Okay, question from Philip. Almost anything related to multiphysics between neutronics and THCFD in industry to not just be initial exploratory design for nuclear would be required to be QL1 under NQA1. And he notes that there's a lack of V and V under NQA1 given the reasons given. Is there any plans for Cardinal and OpenMC NIC-RS to be put through the SQA process under NQA1?
Yeah, great question. So we do have ongoing work at Argonne to bring Cardinal under the NQA1 compliance. And so we're starting that effort with NIC-RS. And so currently, I'm happy to send Philip some of the summary reports from last FY describing this progress. And so right now, we're just currently trying to get everything conformal to that standard, which includes adding more test cases, documenting the test cases that we do have, integrating the SQA capabilities within Moose into Cardinal as well. And so we're making a lot of progress on that. I do note it. I completely agree. It's very important that we have that, especially when we're combining these tools together.
Thank you. Question from Alexis. Are there any plans to add adjoint capabilities to OpenMC for system kinetic parameters?
In terms of continuous energy particle transport, not at the moment, but right now we are looking into that, the adjoint kinetic parameters in particular, based on just tally results and tally derivatives. But so that's in terms of like the tallies, you can kind of compute those that way. But in terms of adjoint transport, we just enabled capability for random ray transport within OpenMC, which is multi-group based in terms of the energy domain, but it is much easier to compute adjoint or to perform adjoint transport with that by just inverting those cross sections essentially. So very soon we're hoping to support adjoint transport directly.
Okay.
At least in the form of random ray, I should say.
Thanks. Question from AJ, is Coreform Cubit available outside the United States? It is. So Coreform Cubit is the commercial version of Qubit that's developed by Sandia National Labs. We try to keep those two pieces of software very similar, but some of the enhancements that we made to Coreform Cubit are distinct to Coreform Cubit, and this OpenMC DAGMC workflow is one of those unique enhancements that's only available in Coreform Cubit, and that is available worldwide.
I've also just dropped a link. If you are curious, we have our export policy that you can get to through our homepage, and in the far bottom right, there's a link to the export policy. So there are some U.S. laws that Coreform is subject to. So you can find more information there.
Great. Thank you, Greg. Okay, just a few more questions to get us to the bottom of the hour. Alexis says, are there, okay, so we already answered that one. Ibrahim, how sensitive K-effective to the fidelity to the mesh?
Yeah, this is a really good question, and something we've looked at extensively in DAGMC. So this is where the faceting approximation, or what is also referred to as the faceting tolerance, comes into play. It's really important because that essentially defines the difference in your volume between the analytics or the analytic part and the meshed part. And so to the degree that we care about the K effective to, the nearest percent mile, we would also want our faceting to approximate those volumes in particular to that, to that level of fidelity. So like to preserve, essentially what it means is like to preserve your K effective value or an integral tally like that to, the fifth digit. Then you would need your faceting tolerance to be close to the fifth digit, which does mean a lot of elements in some cases. And that's all in terms of model units. And the reason for that is that when we perform our track length tallies through OpenMC, that is really the adjustment to the track length that those particles are experiencing, and it directly translates to the tally in terms of the estimator. So,
thank you. Question from Ibrahim: are the capabilities of Moose similar or compatible with ANSYS?
I'm not a direct ANSYS user. Is anybody, Patrick or Matt, are you an ANSYS user? Before I try and answer.
No, I'm not.
Okay. So I would say that they're probably similar. So ANSYS is like a generic package for doing a lot of fluid flow and other coupled physics, similar to COMSOL. So Moose has a very, very wide suite of physics applications in it. Many of them are open source in the framework. So there's a Navier-Stokes module, a thermomechanics module. There are material properties for fluids and solids. There are an upcoming, subchannel module for fluid flow for nuclear applications, in particular, porous media. And so there's a lot of common physics that are immediately available when you download Moose. In addition, Moose has a very wide array of applications which tackle some more nuclear specific use cases. And so something that Moose has, which I don't believe ANSYS would have, would be all of the neutronics capabilities. So deterministic neutronics is in an application called Griffin, which you can apply for through the NCRC organization, or Cardinal if you wanted to do this with Monte Carlo neutronics. And so some physics that are nuclear specific would not be in ANSYS. From personal experience too, I find, getting support for any Moose related questions is awesome. The team that they have is very interested in getting the software into the hands of industry and supporting use cases there. And it's open source, so you can contribute back to it, features that you need for your custom analyses or to extend in other ways. And so those aspects would be different between Moose and ANSYS. And there was a second part of the question, but I slipped my mind.
No, I think that's it.
That was it? Okay.
Thanks. Question from Jin: how does the workflow scale? For example, would one be able to convert the ITER CSG model to CAD, run OpenMC on an ITER DAGMC model?
Yeah, that's a good question. These are relatively new tools, so we haven't hammered on them quite to that extent. I wouldn't say ITER has some of the, especially lately, if you look at the Nature papers, they have some of the most detailed CSG models that have ever existed. We haven't run something like that through our adapter yet, but we have done some of the previous ITER C-Light models as benchmark models to make sure that we can handle those complex components. We have some images of those, and I could put them on the discussion page after the forum. We haven't taken that as far as to do multiphysics with those generated CAD models yet, but that's on our roadmap real soon.
Okay. We'll have this be the final question, and we can direct additional questions to the Cardinal discussion page that April has linked here. This is from Leftherios. The mesh generation seems to be quite cumbersome for just one region. If you have adjacent regions separated by a single surface, how does the code handle possible overlaps between the meshes? Do you have to mesh each region individually, or is there an automatic way to mesh large models to ensure no overlaps?
So I saw Greg unmute, and I'll let him take it, I think, because he's going to know those features way better than I am. But Cubit has a lot of native capabilities in this area. So
yeah, and I guess my question would be what's meant, maybe Patrick, maybe but what's meant by separated by one surface? If the surface is meant to be shared between the two bodies, there is functionality in Cubit we call imprint and merge. We can go into that in more detail on the discussion page. That will guarantee that you only have a single mesh with no overlaps that then is shared by the two volumes. If you have a small gap and you mean for these to be separated, the triangle meshing functionality in Coreform Cubit does have options to find overlaps and remove the overlaps. So that's also something that we could go into on the discussion page.
Yeah, and I'll add on to that for this particular workflow that we were looking at today, where the models are originating in CSG. Neutronics is not happy with overlaps generally, and we have ways of detecting that also. So assuming that your CSG model is well formed, when you bring it into CAD, there should be no overlaps, and there may be coincident surfaces, as Greg mentioned, but those can be imprinted and merged so that they are then shared in the resulting CAD model.
Okay. And actually, there's two other questions that came in that maybe we can address quickly. From Libin, who uses ANSYS, can you export a mesh in INP format from ANSYS to ANSYS from Cubit? I believe having a matching mesh from neutronics heating would be good to connect to structural analysis in ANSYS. Greg, do you want to answer that one?
Yes. So I don't know about the .inp format for ANSYS, but we do support like the .k file, and we do support ANSYS. I think is it CDF or something like that. But we support generally ANSYS mesh export. So I'm not INP. I thought was Abacus format, but if that's just a different extension of the standard ANSYS mechanical mesh formats, then yes, we generally support that.
Great. Then we'll end with this question from Michael. It seems that the workflow depends on DAG-MC. Is that separately developed, and is there a commitment to maintain compatibility between DAG-MC and Coreform? Patrick, do you want to talk to that?
Yeah, I'd be happy to. The short answer is it is developed separately from those packages. It's meant to be like a generic interface to Monte Carlo particle transport on these surface meshes. And there is definitely a commitment to maintaining that interface. It's an ongoing effort. The package is relatively stable at this point because it is supporting what's needed in the community for now. But we're always looking to build in some new capabilities, new mesh specification and library formats, things like that.
Okay, well, thank you again, Patrick and April, for your preparation and time in the webinar. Thank you, everyone, for attending. Have a great day.